Hello all. So I guess that we will wait for a couple of minutes and then we will start.
That's fine. That's fine.
Dear Professor Russchenberg, hello. So
Hi.
how are you?
I'm fine. How are you?
Fine as well, thank you. Today, by the way, we have a national holiday.
Oh, okay. Bad timing.
Professor, I'm sorry. Can we check the audio, please? Because it seems there is echo or something like that. Can you say something?
Yeah, of course. What do you want to hear?
Maybe can you put the micro a bit closer to you, or it's embedded?
What's the problem? Is it better like this?
Yeah, it's better. Thank you. It
Okay.
seems
Okay.
just the room has an echo, and if you speak a bit closer, it sounds better. Thank you.
Okay. That's fine.
I think that we can start. People is joining, they will join. Obviously, maybe a little bit later. But in any case, I propose to start. So today we continue our lecture series from Professor Russchenberg, one of the very famous professors in Western Europe. So it is a great pleasure for us as a National Aviation University to host these lectures online. So we took two amazing lectures on Tuesday, yes, and today we continue. Today we will receive the last lecture from Professor. So the floor is yours.
Okay.
Let's
Thank you
start.
very much. Thank you very much for the introduction. So what I will do today is I will show how we can combine instruments and how we use this for cloud studies and for in the need for better understanding of climate change. So that's more the scope for today. And let me share the slides for this. This one. You can see my slides? Yes? Okay.
Yes.
I will give a short introduction about how we do measurements and what sort of facilities we have in the Netherlands. And then I'll go into the details of what we want, what we measure and why. And one of the things that I want to talk about is what we call the Ruisdael Observatory. And so some of you may know who Ruisdael was, and some of you probably don't. And he was, for us in the Netherlands, a very famous painter from the 17th century. And why he's famous, and you can see this on this painting, he really was one of the first to go out in the field and measure and try to make and paint the sky as realistically as possible. So he really looked at how light interacted with clouds and how light and clouds together interacted with the land surface. So what you can see here, for instance, the bleaching fields, where in those days people put linen on the fields to clean and to brighten. And you can also, if you look at the back over here, you can see the city. He even tried to paint how light is reflected by the rooftops back then. So he was a very almost scientific painter of those days. And that was an example for us, so that's why I picked his name as the name for the observatory. But today we do things differently. Today we make simulations of the atmosphere with all sorts of models. Where we try to model a cloud, as you can see. You can see my mouse moving? Yes? So we try to make models of the clouds over here and how this creates a shadow on the land surface, but also how the cloud is connected with the blue part over here to vertical transport of water vapor into the atmosphere, and how the cloud is connected to vertical velocities in the atmosphere. That's the red part over here. But that's what we try to understand with models. But of course, we also use remote sensing equipment like radars and lidars to measure these clouds. And we use in situ observations like weather balloons with all sorts of instruments attached to the balloon to measure the properties of clouds and aerosols and the atmosphere. The future will be a bit different. The future will really move into the direction of high resolution models. And this, on the left, you can see a forecast of a cloud field over the Netherlands 24 hours ahead with a very high resolution, something like 100 meters. And on the right side, you can see the satellite observations on 24 hours later, so at the forecasted time. And you can really see that the models will, and this is already 5 years ago, that the models, atmospheric models, forecast models, really improving in capturing small details of, for instance, the cloud patterns itself, which you can see over here, the land surface, the ocean-sea interaction, all those details are picked up now also by models. So there's really a revolution going on in more detailed simulations and observations of the atmosphere. Partly this revolution is due to increased computational power. It's a really big driver of this. So why do we do this? Well, this type of knowledge, this type of observations, these type of models are very important for understanding climate change. Because ever since the 18th century, we have changed the atmosphere by putting more greenhouse gases into the atmosphere. And this has led to a cycle of connected events of the water cycle has changed, so clouds have changed, the rainfall patterns have changed, temperatures have changed. And we have to understand all these changes. And for this, we really need more observations. And these observations are now coming down to understanding details of the atmosphere. So if we look at this image, for instance, if you look at this cloud over here, well, this cloud is not something on its own. It's connected to what's happening on the surface. So you have to understand the processes at the land surface. How is the land surface emitting energy and absorbing energy? Because this leads to vertical transport of energy into the atmosphere. And you have to understand also how vegetation is releasing water vapor, or how vegetation is absorbing greenhouse gases. All these processes have to be understood. And what also happens there, when gases are released into the atmosphere, we have all sorts of atmospheric chemistry processes leading to what we call aerosols, tiny dust particles. And what you see later on today, these aerosols, the dust in the atmosphere, is extremely important for the formation of clouds. Because every cloud droplet in the atmosphere is grown around a small dust particle. So all these connections have to be understood if you want to increase the validity of atmospheric models. This is an example of where we have vegetation. But also cities are important because what we see is that in the cities are really expanding. We have many more metropolitan areas with tens of millions of people living there. Well, city is not green, it's usually concrete and brick. And it's much warmer than the atmosphere, and it changes the atmospheric dynamics. And also this is an effect we have to understand. So what we do in this, we look at all these processes in detail. So we've proven these models for different surfaces, land surface, green surface, urban areas. And we try to understand how the cloud over here interacts with the light received at the surface. Because the light received at the surface will also determine how much the surface will be warmed up by the sun. And that's really the driver here. And what we also want to understand is, but that's also the reason why we have to go to these high resolution models and observations, is because even in a small country as the Netherlands, we already see a huge spatial variability of weather patterns. This is an example of the annual distribution of rainfall over the Netherlands. And what you see here, that the coastal part has much more rain than this part in the southeast. And so even on small scales, we see this variability. And this is partly due here, because this is closer to the sea. And the sea is slowly warming up, producing more water vapor in the atmosphere, and therefore more rainfall in coastal areas. And this is also where we have most of the cities in the Netherlands. And the city, if it's warmer, leads to more rising air masses. Well, the air masses rises up, it condenses, and we get clouds and rainfall. So all these aspects have to be understood if you want to get more deeper understanding of the interaction of light of land in the atmosphere. Another driver is that in a warmer climate, we can expect more extremes and more extreme rainfall. One simple driver is warmer air can contain more water vapor, and that is something like 7% per degree of warming. So every degree that the Earth gets warmer, or country gets warmer, or the atmosphere gets warmer, you can expect 7% more water vapor, and more water vapor will lead to more rainfall. Well, this is an example. These are statistics that the blue line are statistics of the precipitation per hour and the probability of this. And what you can see, the blue line, for instance, that you have a probability of less than 1 in a million of getting 50 million meters of rain per hour. This was before 2000. After 2000, the year 2000, we can see a much steeper slope. It went from 7%, which is the blue line, to 15%, so much more after 2000. So climate change is also accelerated the degree to which we have more extreme precipitation. And this is also something we need to understand. So what's going on here? And how can we put this into the models to get a more accurate forecast of this? So what do we do here? And then I'll move into the measurements later on. So we have installed a couple of observatories in the city of Rotterdam, near Cabau, which is a station in the central part of the Netherlands, with many advanced instruments. In an area called Lobos, which is in a more area with forestry, where we have instruments. And in the north of the country, we have a site called Lutjewat, close to another sea, where we have a coastal area where we have also instruments. And this is the map of the Netherlands with the 4 stations in there, where we do these measurements all the time to understand these physical phenomena I just described. So let's have a closer look at how clouds can respond to warming, what we can expect over them. So suppose at present day, we have such a cloud deck, right? And the cloud deck, well, the sun is reflected, so the sun is shining, it's reflected by the cloud top. So part of the incoming light is reflected, and part of the light reaches the surface of the Earth. But in a warmer climate, we can have thicker clouds because we have more water vapor. That's the mechanism that can happen. Well, thicker clouds reflect more sunlight. So that will be a negative feedback. So more warming will make the clouds thicker, and the thicker clouds will lead to more reflection. That's more cooling. So there will be compensation effect. But we also can have the situation because of more warming, more evaporation of clouds. So then the clouds become thinner, which means they will reflect less sunlight, and this would amplify the warming again. So that's counterproductive. And we might have the situation that we have that the clouds break up in smaller segments because of increased convection from the surface. Yeah, then we have open spots where the sunlight can directly shine through and hit the surface of the Earth. Also, this will be a positive feedback. And now the trouble with clouds in the climate system is all these 3 occur at the same time. And it depends on where you are at the globe. So it's a strong regional dependence. So why do clouds do this? Well, if you look at clouds, then of course every cloud is composed of droplets, right? And every droplet reflects a bit of sunlight. All these reflections together lead to cooling. Clouds also absorb heat radiation coming from the Earth, right? And part of this is then emitted again to the universe, but part of it is also emitted back to the surface of the Earth. Well, that leads to warming of the surface of the Earth, and that's a warming effect. But clouds also, if you look at clouds, well, you see they change continuously. That's because they evaporate continuously, and there's continuous condensation going on in clouds. And at the same time, these clouds are moving. So during evaporation, the atmosphere cools, and because the cloud particles themselves get a larger motion, kinetic energy, and this is removed from the surrounding air, so the air cools. Condensation, well, then the clouds get less, the particles get less kinetic energy, they lump together, and then so they lose energy to the surrounding air. So condensation processes warm the air. And this means that clouds also distribute energy across the globe on a larger scale. That's the complexity of clouds in the climate system. Well, and you can understand that to improve the models, the climate models and the weather models for these phenomena, you really have to come up with many observational strategies to do all the measurements on different locations. So that's one part about clouds. Another part about clouds is the link with dust particles, so clouds and aerosols. And well, this is a graph of typical sizes of cloud droplets in the atmosphere. They usually start with a tiny particle, what we call a cloud condensation nucleus, particle of less than a micrometer, something like a tenth of a micrometer. And throughout the growth process, they become haze. Then we have a cloud droplet here, 10 micrometers. The drizzle droplets, a very light rain, around 100 micrometers, and then the raindrop, something like 1 millimeter. So along all these scales, so from the smallest one to the largest one, all these particles occur at different scales in the atmosphere. And it all grows around a single dust particle. How does this work? And that's an important part to understand. If you look at, on the one hand, water vapor, then we are always taught that if you look at the condensation from of water vapor into a liquid, that the moment you have equilibrium between the gas phase and the liquid phase, we talk about saturation, and we call this 100% humidity, right? But this is only true for an extremely flat surface. The moment you bend the surface, like in a droplet, then of course the surface tension becomes weaker, and it's easier for droplets to escape the liquid into the gas phase. It also means that you need more water vapor around the droplet to get equilibrium, to get saturation again. And then we talk about supersaturation. And that's the important part, because if you look in the atmosphere, it will be practically impossible to form a droplet just based on condensation of pure water vapor alone. Because you talk about 10,000% or so of supersaturations you need. So in nature, cloud droplets do not form by themselves. They need help. And this help is coming from dust particles. But the moment you have, for instance, a sea salt particle or salt particle in the atmosphere, they will attract water vapor. For salt is very what we call hygroscopic. That means, well, water vapor, dust particle attracts the water vapor, and then it becomes easier for a cloud droplet to form. Well, the relationship between particle size, so the droplet size, and supersaturation is given by this Euler curve here. What it means is, and that's what you could see over here, if you have a particle, a dust particle here, of this initial size, a small size, and the green line gives you the humidity of the atmosphere. Well, the humidity of the atmosphere is higher than the humidity where this blue particle is right now. The particle can grow, right? And it can easily grow along the black curve. And once there's a black curve, it becomes a large particle and turns into a cloud droplet. But the moment you have dry air, so suppose your environmental air is dry, then if you have a dust particle here, well, it grows along the Euler curve, it hits the green line, and then it cannot grow anymore. There's no water vapor available anymore. So it sticks to a very small particle. So it means in nature, if you look at the formation of cloud droplets, you need a certain amount of environmental humidity, so water vapor in the atmosphere, because if that's too low, then cloud droplets won't form. And that's a very important aspect. It also means now that if you want to understand the formation of clouds, you also need to understand the relationship with aerosols, with dust in the atmosphere. And this relationship, cloud droplets and aerosols with dust in the atmosphere, are one of the biggest challenges and unknowns in climate studies. And many observational tools have been developed to study this. And to wrap it up, how the whole process works is that if you start at the surface of the Earth, with some dust in the atmosphere, and it might have this distribution, side distribution, so small particles here, large particles there, then these particles will be uplifted by convection, or wind in the atmosphere. At some stage, at some particular height, they will reach the surface at which there is enough water vapor around, so condensation can occur, and then the particles can start to grow along this curve over here. But it's only true if the aerosols from the cloud at the surface themselves are big enough, because if you are too small, then they won't grow into this cloud phase over here. So there's a really strong relationship between the properties of dust at the atmosphere, at the surface of the Earth, and cloud formation above. So apart from temperature, humidity, and water vapor itself, for cloud formation, you also need to understand how much dust you have in the atmosphere. And that's important because this dust might be natural, might be man-made, coming from the industry or so, and this will all impact the cloud formation, and therefore also the relation with climate. Because what happens, suppose you would have the cleanest form of air in the atmosphere, so no dust at all. Well, then it's impossible for droplets to form. You need dust, so no aerosols in the atmosphere also means no cloud. It's this gray block over here. And if there's no cloud, well, there's no albedo, no reflection of sunlight. Or wrong direction. Now, suppose you have clean air, just a few aerosols, so just a bit of dust, then this might rise up until it reaches the level where clouds are, and then this small amount of dust particles in the atmosphere, well, they have all the freedom to collect all the water vapor around them. So they can grow into large droplets, because they can take all the water vapor. But that will be a cloud with a small number of droplets, but large ones. Well, if you do the calculations, they will reflect sunlight, but not so much. If you look at this case, so many aerosols, so polluted air, then this will rise up. At some stage, it will reach the height of the atmosphere where clouds are formed. And then this large amount of dust will have to compete for the amount of water vapor around it to grow into the cloud droplets. So what you get are many small droplets. Many small droplets, they will reflect together lots of sunlight, and you get a high albedo. So depending on how much dust you have at the surface of the Earth, the clouds will reflect no or high or low, no sunlight or high amount of sunlight. But there's a direct relationship. This is an example of a simulation we did, and then I moved to the measurements. So on the left panel here, you can see a top view of a cloud deck, and every small spot in here is a cloud, and every dark spot in there, that's a hole, the space between the clouds. and then you see the sea surface. And what we do, we say, well, we have the same initial condition for a cloud field, but in this case, the upper panel here, we start with clean air from below, so a low number of aerosols. And the bottom one is a high number of aerosols from below. And then we see in the simulation how the cloud field develops over time. And you see they're completely different. So this one over here is completely different from that one